I handed it out last time. Did you get a? Yeah, you were here Friday. Kind of a thick packet. It's got a huge number of bullets at the top of it. Sometimes I didn't bring any copies today, and I can't remember. Is everybody except Gracie and Alvis here on Friday? Can't remember if Jake Woosley was here or not on Friday. I think he was here. Okay. So we've got just a couple more things in chapter 3 to finish up, and then we'll head into chapter 4, which will maybe feel like a little bit of a nice break from chapter 3. Chapter 3 is very formalized, lots of mathematics in it. Chapter 4 is back to calculation, but we're moving into 3 dimensions, separation of variables, as you saw, and solving differential equations and trying to match boundary conditions. So things will either get better or get worse, depending on how you feel about them. The end, so last time we were talking about finite dimensional vector spaces and writing the components of a vector as a column vector, and you know, the operators are n by n matrices, and we solved an eigenvalue problem and put some time dependence in it. And today we're just going to talk more generally about when we say Dirac notation. That specifically means not just denoting a vector like this, but dividing up the inner product into 2 pieces. And because it's a bracket, Dirac called this the bra and this the ket. So the ket is just a regular vector, just a different notation for a vector. And then the natural question is, well, what does the bra correspond to? And the answer is, well, it's something that is like a vector that is saying, I'm ready to take an inner product with something. You just put a vector next to me and I'll give you a number. So it takes in a vector and it gives out a number. That's what a bra is. And the name for that is a linear functional. Especially if we're talking about functions, if this vector is a function, then usually people will call this a linear functional. It's something that takes in a function and gives back a number. Just for example, how this looks in various contexts. If we're using our finite dimensional vector space, representing things as column vectors like this. So here I'm imagining a 5-element column vector. What would the corresponding, or what would a corresponding bra look like? Well, the idea is it should give well, let me just tell you the answer. The answer is you write it as if you know the corresponding vector that you want to take the inner product with, instead of writing it as a column vector, you write it as a row vector and you take the complex conjugate of all of them. And that represents the bra in this Dirac notation. And that's because when you place that bra next to a ket, you can't help but do the matrix multiplication that's implied there. And that's exactly what the inner product is for a finite dimensional vector space, right? You sum together the products of the corresponding components with a star on this one. Okay, so that's what it looks like in a finite dimensional vector space. In an infinite dimensional vector space, well, if it's an infinite dimensional vector space that has an infinite but discrete collection of components, it kind of looks the same. It's just an infinite row vector like that. If it's an infinite dimensional vector space with continuous components, in other words, like our good old psi of x kind of representation of a vector, so we're representing a vector by a function of x, then how do we think about the corresponding linear functional, which is ready to take in a vector and turn it into a number? Well, it's sort of awkward to write it. We say, what is the linear functional that corresponds to the vector g of x? Well, we take the complex conjugate of it, and then we have to leave a little blank here that says I'm ready to take in a vector in function form, and then I integrate from minus infinity to infinity. That gives me the inner product. So again, this is the corresponding linear functional that takes in a vector and gives a number back as the inner product. Now, one of the reasons we call these things vectors is because together they satisfy the axioms for a vector space. And so another piece of terminology that often comes up is, what do you call the collection of all linear functionals? Well, the idea is, if you think about those linear functionals, they form a vector space too. You can think about, if I have a linear functional and if I multiply it by 2, or if I add linear functionals, you can make sense of that, and they will be closed under addition and scalar multiplication by complex scalars. So they are a vector space too. The collection of all linear functionals is another vector space, and people usually call it the dual space to the original vector space. So you've got a vector space, that's a collection of vectors that you're considering. There's always a dual space, which is the collection of all linear functionals on that vector space. You have to have a scalar product defined to make sense of that. So these are just some things that Griffiths mentions very quickly at the end of the chapter. I'm not sure how much he said on this, not as much as I'm saying here, but suppose Q has, the operator Q has some matrix elements, and I'm not assuming Q is Hermitian here. Okay, so it's got some matrix elements. It's maybe a 5 by 5 matrix with numbers in it. Okay, how do I figure out what the matrix element of the Hermitian conjugate to that operator is, or the adjoint to that operator is? How do they relate to it? If you give me the matrix elements, how do I figure out the matrix elements of the Hermitian conjugate? Anybody remember the answer from the reading? I guess that was a while ago that you read 3.6. If I give you a bunch of matrix elements, let's say it's a 2 by 2 matrix, this is the question. Suppose Q is represented by matrix elements. We'll make it a 2 by 2 operator, kind of like the ones we were doing before. 2, 3 plus 7, I'm just putting some random numbers in here, minus pi minus 4.2. Okay, there's an operator on a 2-dimensional vector space, right? Not necessarily Hermitian. The question I want to know is, how do I get the matrix elements of Q dagger, the Hermitian conjugate to it? Anybody remember just what the final answer is, and we'll show it? The answer is, you take what's called the transpose of the matrix, so you flip it along the diagonal, okay? And then you also take the complex conjugate of every number in it. So it's called the transpose conjugate. So this corresponds to matrix elements. Diagonal stays the same. The 3 plus 7i goes down here, and it turns into a 3 minus 7i. Pi is perfectly real, so I don't have to take its complex conjugate. So that is called the transpose conjugate of that matrix. And the Hermitian conjugate matrix elements are the transpose conjugate of the original operator. Here's the justification. So let's assume that we know the matrix elements of Q, they're QMN. And we want to find out what Q dagger MN and how it relates to QMN. Well, let's just start out with Q dagger MN, write down by definition what it means. So Q dagger MN means sandwich Q dagger between FM and FN in whatever basis we're talking about, right? You always have to say, when you're getting matrix elements, you have to have in mind some basis that you're using. Here, I haven't thought too much about what that basis is. It's not really going to matter what the basis is. And then we are going to put this Q dagger over on the left-hand side using that property of the inner product, which says if you switch the two sides, you can put a star on it, and that's all okay. Why do I want to do that? because now I've got the Q dagger on the left, and by definition, that is the same as putting just the plain old Q on the right, right? By definition of the Hermitian conjugate. Forgetting about the star for a second, just a Q dagger over here is the same as a Q over there. Doesn't matter what the operator is, doesn't matter Hermitian or not. And by definition, this thing under the star here is the NM matrix element of Q. So I've related the NM matrix element of Q to the MN matrix element of Q dagger. So that means, you know, Q dagger has in its 3-1 position what Q has in its 1-3 position, but complex conjugated. If you think about that, that's the transpose conjugate of the matrix elements to get the matrix elements of Q dagger. Okay. Again, just a couple grab bag things, but people asked about them. I'm still rather light on the reading responses. I think there were 2 people as of Friday who had done the reading responses for 3.6, but I'll try to address some of the questions that were in there. Griffiths also mentions projection operators in building up a structure that is useful to us sometimes. Well, maybe it's best to introduce it on the board in the context that we're more familiar with. Suppose I said, I'm thinking of a unit vector. We're in 3 dimensions, maybe. Let's call it x hat, right? Suppose I did the following. I said, I'm gonna form something that says, whatever vector you give me, I'm gonna take the inner product with x hat and then scalar multiply x hat by that resulting number, right? When you take the inner product, you get a number, and we're gonna scalar multiply x hat by that number. How would you describe what that operator is doing? Well, this we can think of as just the x hat component of a vector, right? If I say this is going to operate on something, right? So you're going to put a vector into it. So some arbitrary vector in 3 dimensions. V, this takes the x hat component, right? And then we put it in front of an x hat. That's kind of like, at least if I draw a 2-dimensional kind of diagram here, let's imagine x hat looks like this and y hat looks like this. And well, let's not draw it exactly at 45 degrees. This is what my arbitrary vector v looks like. This distance right here is v dot x hat, right? Or I guess I wrote it before as x hat dot v, doesn't really matter if we're talking about real vectors. And then if I scalar multiply by x hat, I'm saying take this multiple of that unit vector, and that would be a vector that points along the x direction, but has exactly this length. So this is x hat dot v. And so people sometimes call this operator that's ready to take in a vector a projection operator, because what it's doing is it's a certain kind of projection operator. It's projecting onto a subspace of a vector space that's spanned by just this vector. So it's saying project any vector you give me just onto the x direction, right? Take the shadow on there, but still leave it a vector, right? Still, we're going to end up with a vector. It's not just the component, it's because components are scalars, but it's the vector projection, kind of the shadow on that axis, right? Okay, so same thing in an arbitrary vector space. You know, this could be an infinite dimensional vector space, but if we take a single normalized vector, it's got to be normalized or it won't be a projection operator, right? It was crucial that this was a unit vector, that we took the inner product with there. The projection operator in Dirac notation looks a little bit weird and kind of backwards. Looks like a backwards inner product. But what this is saying is, if you put a vector v next to this, it's going to take the inner product of v with alpha. Isn't that what we were just doing right here with our x hat? We took the inner product of the vector you took in with that, and then that number is going to scalar multiply that same vector, unit vector, back again. So that's what we call a projection operator. It projects onto the line that contains alpha, if you're thinking geometrically, or sometimes in terms of linear algebra, you would call that the one-dimensional subspace spanned by alpha, whatever line alpha lies in. Similarly, if we have, maybe we're in an infinite dimensional vector space and we choose 7 different orthonormal vectors. So not only are they all normalized unit vectors, but they're orthogonal to each other. So it would be like we're in a 10-dimensional vector space and we choose the first 7 of an orthonormal coordinate system or something like that. Here's a different kind of projection operator, right? This would be like you could project this vector onto the x-axis the same way we did here. Also project it onto the y-axis and add those two together. Well, if I put in a vector that was a 3-dimensional vector, it would project that vector onto the 2-dimensional space that contained the 2 vectors we were taking the inner product with. So this is projecting onto what people would call the subspace spanned by those unit vectors that are orthonormal. Okay, so it's a kind of projection operator. There's lots of good reasons to be interested in them, but Griffiths only really mentions one of them. And that is, we're going to build the identity operator out of projection operators. And you could think, well, maybe we were in 2 dimensions here. What if I project a vector onto just the x-axis? That's one thing. But if we're in a 2-dimensional vector space and I project it onto the whole space, in other words, I project it onto the x and y and add them together, I haven't really done anything to the vector, right? It's sort of like saying, project this vector in 3 dimensions onto the 3-dimensional space. It's already done. It didn't do anything. That's called the identity operator. And I can't remember if I'm following Griffiths' notation here, but I tend to write it as a 1 with a hat on it. It's the operator that if you give it any vector, it doesn't do anything to it. So it's kind of one of the least interesting operators, but we're going to find when you look at it in the sideways kind of way, it actually can be quite interesting. Okay, so the identity operator doesn't do anything to it. It just projects onto the entire vector space, and that doesn't change the vector at all. Why do we care about it? Well, if we have an for example, if we have a discrete orthonormal basis for our vector space, we can form the identity operator by projecting onto the entire space, right? So I'm going to imagine En is an orthonormal set of vectors that is complete. And therefore, this is just saying, hey, project onto the entire vector space. That's a different way to write the identity. And this is called the resolution of the identity. It's unclear why you'd want to do it, but we'll show it why in just a second. Similarly, if you have a continuous complete Dirac orthonormal collection, right? That we've seen lots of examples of this. These would be like our scattering functions in the position representation. Then the resolution of the identity is just like we had to add sum over all of them over here. Here we have to integrate over all of them. And this is an operator that's ready to take in a vector, and it's going to project onto EQ and then scalar multiply that number, EQ by that number that results, and add them up over all Qs. And that's also a different version of the resolution of the identity. Here's why we might use the resolution of the identity. It's a great way to figure out the formula for how to compute a lot of different things if you forget about them by starting with just abstract notation. So, for example, if I denote an abstract vector like this, that's kind of hard to know how to think about that vector. In order to specify a vector, usually we have to give it in a particular representation, right? If I want to tell you what state a particle's in, I can't just say, hey, it's in a state, and I give a Dirac ket like this. That gives almost zero information other than a symbol we're going to call it by. You would have to give some psi of x or something like that in some representation to communicate the information. Well, of course, that vector is nothing but the identity multiplied by itself, nothing profound about that, but we're going to write the identity in terms of a particular resolution of the identity. Remember, I said for the resolution of the identity, you could use any orthonormal basis like this, right? So let's imagine if we're in the context of the harmonic oscillator, well, infinite square well, since I'm starting at n equals 1 here. Infinite square well solutions, and we would say our energy eigenvectors span the space and they're mutually orthogonal and normalized to each other, then this is a perfectly good way to write the resolution of the identity. There are lots of different ways to write it. And notice that when I'm saying our original vector is written as a bunch of numbers, these are the numbers, times those basis vectors, and the numbers Cn, we usually call them Cn. This tells me how to compute the Cn's straight away. I didn't even have to do any Fourier tricks or anything like that, right? It's saying, if you want to expand something in terms of ENs, these are the expansion coefficients. And that's an inner product. If somebody gives me the position representation of this function, and I know the position representations of all these ENs, I can calculate the CNs. Okay. Similarly, in the continuous case, if we have an abstract vector and just write it as 1 times that, let me write a very particular form of 1, which is the resolution of the identity expanded in terms of momentum eigenvectors. And in that case, we would call, when we expand a state in terms of momentum Dirac orthonormalized basis vectors, the expansion coefficients we usually call the momentum space wave function, which is the momentum space components. So that's telling me directly how to compute it without having to do any tricks or anything like that. That's one reason the resolution of the identity is kind of useful, even though it seems like on the surface it does nothing. It also reminds us how to calculate, or explains very quickly how to calculate components of an operator. And again, when we're using the resolution of the identity, we tend to start out with an abstract description of something, and then we change it into the same description in a given representation. So for example, here we're saying Q turns some vector alpha into some vector beta. We can get out of that how to compute the matrix elements of Q in a particular representation. All I'm going to do is sandwich the identity operator between Q and alpha. That's just saying 1 times alpha gives alpha back again, so that hasn't done anything. But now I'm going to write that 1 as a particular version of the resolution of the identity. Here I've summed over definite energy eigenvectors. Okay. There's still some abstract vector stuff in here. So in order to get rid of the vector stuff and have something that's in a particular representation, we're going to take the inner product of both sides with another state EM. And when we do that, we can see that in the energy representation, the statement that's equivalent to this one is when you matrix multiply these matrix elements times this column vector, you get this column vector. And that's reminding me, if you've forgotten, either how to compute the matrix elements or why they're directly related to statements like this. Okay, so they tell us about matrix elements, they tell us about expansion coefficients, always starting out with the abstract statement. So, well, yeah, that's what I just said. A couple of people asked about these, so I'm not sure what XX is representing. What this means is this is something that is ready to operate on a vector. In other words, if I put a vector over here, it will take that vector's inner product with a state of definite position. It looks like that notation is suggesting, and then scalar multiply that number times that vector. Okay, so that's a projection operator. And the resolution of the identity, well, we just explained what that has to do with. Any more questions on those last couple of just things that are the very end of the chapter? Griffiths, maybe it's relegated to some of the homework problems, and I probably didn't assign any homework problems that required you to use the resolution of the identity. But it is something that's useful, especially as a desert island technique where you've forgotten, wait, how do we get those expansion coefficients? If you remember the resolution of the identity, you can get a lot of representation dependent stuff just by writing down abstract vector statements. Okay, so, and we're now ready to go into chapter 4. Any more questions on the chapter 3 stuff? Good, okay, so this will feel like something completely different. In class, I handed out the notes for chapter 4. I haven't put them on the website yet, so I'm sorry to those of you on Zoom. I'll try to put them on by tomorrow at the latest. I just printed them out today before class when I realized we were going to get into chapter 4. So you get this, and you'll see that the images here are not really skipping anything that's in the notes. What you're seeing here is what appears in the notes. And we want to talk about solving problems in 3 dimensions and what the time-dependent Schrodinger equation talks about in 3 dimensions, and how we get a time-independent Schrodinger equation that will help us solve the time-dependent Schrodinger equation. Okay, so we've got some operators. Out of laziness here, I didn't put the hats on here, but really they should have hats on them. Just like px is minus I h bar ddx, similarly for py and pz. And sometimes we denote the momentum operator as a vector operator, and it has components, if you like, Cartesian components. And it's denoted as minus I h bar times del, where del is called the Laplacian. And we think of it as, I don't know if you encounter this in modern physics or in your math classes, maybe you've encountered the Laplacian. So we think of del as a vector operator that has, at least in Cartesian components, the following components. D dx is its x component, d dy is its y component, and d dz is its z component. That's called the Laplacian. And it just makes for a nice shorthand notation that, it has these components in Cartesian coordinates. The components are quite a bit more complicated, or you have to think about them carefully, in spherical and cylindrical coordinates. So it looks nice and simple in Cartesian. And you can think of that as defining it, but then we might ask the question later, what about in spherical or cylindrical coordinates? Okay, so in terms of this, the time-dependent Schrodinger equation is essentially the same as what we had before, except that when we have the operator p squared over 2m, it's this 3-dimensional p that we're going to be using, right? So when I take the square of this, I'm sorry, this is called the del operator. The Laplacian is del dot del. I misspoke earlier. The Laplacian is denoted by del squared, and it's defined by del dot del. Okay, well, we don't usually take inner products between things like this and themselves, but you do the same thing. You put a ddx next to a ddx, that gives me a second derivative, right? Added to the product of these components, So it's defined kind of the same way. So the Laplacian is denoted del squared. And if you write p squared over 2m, that means, p dot p over 2m as an operator. That simplifies down to this, or it doesn't even really need to be simplified much. Psi here we're thinking of is a function of x, y, and z, or the spatial coordinates, and time. So our solution is going to be a function of 4 variables, x, y, z, and t. And the potential here, we're going to make the assumption that we kind of did back in chapter 2, that the potential doesn't vary with time. It's a time-independent potential. But in principle, at least at the beginning, it could depend on all 3 Cartesian coordinates. Later on, we'll switch to spherical coordinates, and we'll make the assumption that in spherical coordinates, it might only depend on r, right, if we have a central potential. Okay, and the other side of the Schrodinger equation is exactly what it was before. It's just psi is now a function of those 4 variables. Sometimes we'll sort of lump the x, y, and z together and just say it's a function of position variables and time. When we normalize the wave function now, before when psi was just a function of x, we integrated dx from minus infinity to infinity. Now we got to integrate from x, y, and z minus infinity to infinity of the magnitude squared. Require it's 1, and that gives us a normalization constant. If we've normalized the wave function, then we can calculate probabilities, and probability is like the area under the curve. Well, it's not really an area anymore. If you have a function of, at a particular time, I'm imagining we evaluate psi at a particular time, it's a function of x, y, and z there. And if we calculate the magnitude squared of psi and then integrate that in a particular range of x's, y's, and z's, that will give us the probability that if we measure the position of the particle, it's in that range of x's, y's, and z's. Nothing profound here, just generalizing to 3 dimensions. Okay, now we want to find out something about what these solutions to this look like, and we're going to take the same approach we did before, and in fact, it works out exactly the same way. If we imagine that, I guess I didn't write down the intermediate step here, but we're going to first assume that out of desperation, we already know how it's going to kind of work out in the end, so why this might be justified or useful at the beginning. But we're going to write our psi of position variables and time. We're going to hope that we can separate it out into something that is just a function of the position variables, x, y, and z if we're in Cartesian coordinates, times a function of only time. Right? We're going to look for product solutions. And then later on, we're going to form the general solution out of all of those, just like we did before, but we've got 3 spatial variables. When you do that, of course, things work out in terms of the time solution, work out exactly the same way they did before. So we find out that we get a differential equation for t of t. We solve that differential equation and we get exactly the same factor. Well, okay, I guess I'm misremembering. In Griffiths, this must be called phi of t. Probably not the best notation, given that we're going to start talking about spherical coordinates too. Not the same phi, but it's some function of time. I thought it was capital T of t. Maybe there's something that doesn't match up with Griffiths in there. In any case, we've done the first step of separation of variables. So now we'd say we already know what this function is. Our whole goal now is to figure out what this lowercase psi is. The lowercase psi, after you separate variables, and I'm not showing the details here, but it's not too complicated. It's very similar to one dimension. We find out that when you separate variables, lowercase psi has to satisfy this equation, which we call the time-independent Schrodinger equation. The only difference is that the second derivative with respect to x before is now replaced by the Laplacian. Other than that, it's very similar. And I can't really go any further. Well, I can go further with this, but this equation here depends on the potential. We haven't specified the potential. So to really solve this, we need to know more about the potential. The potential might depend on x, y, and z, or spherical coordinates or something like that. The whole point is that when you solve for all the possible solutions of the time-independent Schrodinger equation, you get a complete orthonormal set of functions, and we can build up psi of r at time t equals 0 by writing it as a linear combination of all the solutions we found to this, and then we can put in the time dependence exactly like we did before. So there's nothing new really to remember in terms of how we basically go about finding these kinds of solutions, which are written as infinite series. The real difference happens in solving the time-independent Schrodinger equation, which is now this potential is a function of x, y, and z, or we're very quickly now going to do it in spherical coordinates because radial potentials are particularly interesting. Like for the hydrogen atom, we're going to imagine that that proton, which is the nucleus, is basically stationary, and we've got an electron that feels a potential as it moves to different locations in space. So there's a potential energy between the positive particle and the negative electron. Okay, so that seems, because it doesn't depend, the potential energy doesn't depend on theta and phi, seems more sensible to put it in spherical coordinates. And our solution is going to be a function of x, y, and z, but we're going to try to find it in spherical coordinates because our first big example is the hydrogen atom. Just a reminder, since this differs from what you see in your math classes, that we're using the physics convention, which says that that angle theta is off of the plus z axis. So this is theta. Phi increases off of the plus x direction and spins around the z axis in that direction. And the vectors, unit vectors, r hat, it's kind of hard to see in this 3D, but r hat is pointing along this bar right there. So at this point in space, r hat points along the direction of most rapid increase of the r coordinate. Theta hat points in the direction of most rapid increase of the theta coordinate. So it's where, when you're out at a point in space, theta hat always points perpendicular to the r direction from there. And phi hat always points around, so it only has non-zero x and y components. Phi hat always has a 0 z component. It's kind of hard to tell from the picture there. Okay, so that's the physics definition, which is switched theta and phi from the math definition, unfortunately, but both of those seem like they're set in stone. So we're going to very quickly, just to simplify our lives, but also motivated by the hydrogen atom, assume that the potential energy function, which could potentially be a function of all three variables, x, y, and z, or r, theta, and phi, we're going to assume it's only a function of r, not a function of theta and phi. That's what we call a central potential. And that's going to help us simplify and continue to separate variables in spherical coordinates by the same kind of process. The first step is, I guess the first step is, well, we've put these things in spherical coordinates. We're assuming our solution is a function of spherical coordinates, but our del squared, that Laplacian, was written in Cartesian coordinates. How do you write it in spherical coordinates? And I'm not going to derive this in class. You can do it by just straightforwardly, but it's sort of painful to change variables from x, y, and z of this operator. What is a second derivative of x, y, and z added together? What does that change to when you change to variables r, theta, and phi? But you don't need to know where it comes from. It's useful to look up sometime or make sure you can do it yourself, even if you don't remember it after the fact. Somewhat complicated, right? I mean, that is not a simple operator. What looked very simple in Cartesian coordinates looks quite complicated in spherical coordinates. But it's going to simplify our lives because we can further separate variables easily here. So again, we're going to do the same thing that we always do with separation of variables, and that is look for special solutions to this equation, the time-independent Schrodinger equation, that are product solutions. A product of a function of r times some other function of theta and phi. Conventionally, that function of theta and phi is given the symbol y. And we separate variables. And I'm not going to go through all the details. I think the details are more fleshed out in Griffiths. Nothing amazing happens here. We do the same thing. We substitute this form in for psi up here. You try to get all the r stuff on one side and all the theta and phi stuff on the other side. And then you make the argument, if this is a genuine function of r, in other words, it's not constant as r changes, then I could change this side, but this side wouldn't get the message, and that wouldn't make any sense. So the only way a function of r can equal a function of only theta and phi is if both sides are equal to a constant. They're not really a function of r. They don't change as you change r, and this side doesn't change as you change theta and phi, okay? Strangely enough, the constant, you could give it any name you wanted. We could have just called it c or something like that. But here, we're giving it a form that will actually make our lives a little bit easier later on. So for right now, just think of this as an arbitrary constant. You could say, well, what if I wanted to have the number 3 plus 4i? Well, there's some value of that script L, complex value of L, that would give you 3 plus 4i when you plug it in. So there's nothing that's less than completely general here. This could be any complex number as long as I allow L to be any complex number. We're going to find out later on that L can't be complex, and in fact, it takes on integer values only, the range of which we'll find out later on. Okay, so we're just going to set these two things equal. This is going to be a differential equation for r of r. This is going to be a differential equation for y of theta and phi when we write those down. That's called the separation process. Since the R equation has the V of R in it, means we can't go any further with it until we're told what V of R is, right? But V doesn't have a theta and phi, so there's no V in this differential equation. And so that one's the easiest one to approach here. We don't really have to know anything about the potential in this particular case. And again, we've got a function of two variables. The usual approach is to, again, try to separate once more. So let's try to write that y of theta and phi as a function of theta times a function of phi, separable or a product solution like that. We usually use capital phi. I don't know, my capital theta looks a little bit strange. It looks like a 0 with an H in the middle, but capital theta usually has those little wings on the crossbar in the middle. Okay, so we take this, substitute it into this differential equation, which I'm not writing down here because I'm trying to give you the high level view so you understand what's going on. And then we try to separate the variables. So we get a function of only theta on one side and a function of only phi on the other side. And lo and behold, it works. And we set those two sides by the same argument. They have to be equal to a constant, and the constant is called m squared here. No assumptions on m. M at this point can be any complex number. And you have to kind of think about that. If m is allowed to be any complex number, then m squared could be any complex number. And so the constant could be any complex number that you like. There's nothing that's less than general at this point. The equation, so when we look at this equation over here, we set the resulting function of only phi equal to m squared. It's a nice simple differential equation. And well, just because I've been talking too much, how do we solve that differential equation? It's also an ordinary differential equation, right? We've finally gotten away from partial differential equation because phi is only a function of one variable. Phi is a function of phi, which sounds ridiculous, but there are different phis here. What's the solution look like? Complex exponentials, second order differential equation. So I'm expecting two linearly independent solutions, right? It's first order, constant coefficient, ordinary, second order, constant coefficient, ordinary differential equation. So it has two linearly independent solutions, and they're the two different varieties of complex exponential functions like that, except that again, this m right here can really be, there's no restriction on it yet. So for now, we're going to assume that m might be any complex number. So that makes these, we think of these as oscillating solutions, but if m is purely imaginary, then this is an exponentially, if m is I, then this is going to be an exponentially growing equation. If m is some complex number, it oscillates, but also increases or decreases its amplitude exponentially as you move along in phi. Okay, so that's our starting solution. We have to apply some boundary conditions to this solution because phi only goes between 0 and 2 pi. So whatever this equation is doing at 2 pi, it better be doing the same thing at 0, right, in order for phi to be continuous. So let's apply those boundary conditions now. When, so phi at 0 is 1, right? When you put in e to the 0, you get, let's see, maybe I better write this down. So we've got our solution a e to the I m phi plus b e to the minus I m phi. Make this as obvious to you guys. Phi of phi is equal to a e to the I m phi plus b e to the minus I m phi. And we're going to require that phi at 0 equals phi at 2 pi. In other words, this part of a big product solution, right? Our product solution is now going to look like this. We're saying we're looking for things of the form r as a function of r, theta, capital theta as a function of theta, phi as a function of the variable phi, times, that time function. I might call that t as a function of t, that complex exponential that we usually have on the end. If this part of it, if this factor isn't continuous, the whole thing won't be continuous. So we got to at least require that this factor is continuous. Okay. So when I plug in phi equals 0 in there, I get e to the 0 is 1. So I get an a plus b is equal to, and let's see, phi equals 2 pi, I get an a e to the I m 2 pi plus b e to the minus I m 2 pi. Now, I was trying, when I looked at my next point in the slides, I was a little bit confused by what happened there. That means e to the I m 2 pi has to be 1. Certainly, the only way this is going to reduce down to a plus b is if this equals 1, and also this equals 1. And the condition that requires that this equals 1 is the same condition that's going to make this one equals 1. So we don't get two separate solutions or restrictions here. I've got, there's only one a to be had, and so its coefficient on this side has to be 1 if this is going to be true. So that means that e to the I m 2 pi equals 1. And well, how do I make a complex exponential equal to 1? Well, the thing that appears next to the I has to be a multiple of 2 pi, an integer multiple of 2 pi, and that means m has to be an integer. M has to be restricted to 0, plus or minus 1, plus or minus 2, and so on. Any integer value. This also has to be equal to 1. If you set it equal to 1, you'll find m has to be integer values there too. So the whole thing works and is consistent, and that makes using those m's makes our function continuous from 2 pi back to 0 again. Okay, so usually, of course, we could have an arbitrary normalization constant out in front of there. So the idea is, again, if m can take on any integer value, these functions take on the same values as these functions. So we don't really need to keep both of them, right? If we allow all integer values of m's, we get, just using this form of the function, we also get those functions too. Okay, so we're going to say our solutions here are things of the form e to the I m phi, where m is restricted to these values, and we're not going to put a normalization constant out in front. That doesn't mean that this is in some sense already normalized. What it means is I only need one normalization constant for this whole big mess right here. And if I'm going to normalize theta as a function of theta times phi as a function of phi, maybe I'll put the normalization constant with the theta function. And I'm just going to leave this one just as a plain exponential to keep it nice and simple. So we're going to normalize later on, but we're not there yet. Okay. Sorry, I'm talking so much. We will have a worksheet in a bit. And I don't think we'll get there today, though. 127. Okay, so continuing on. Okay, that was the solution of the phi differential equation. It was kind of simple. Theta, not so simple. When we have that function of theta equal to the constant m squared, and then we sort of simplify stuff a little bit, multiply by theta on both sides, and put everything on one side with a 0 on the other side. This is what the differential equation looks like for theta as a function of theta. And at this point, you have to, there's nothing simple. This is not the harmonic oscillator differential equation. We have to get serious and look for a series solution. And when you do that, find a series solution for this, the way you at least did a little bit in differential equations. The solutions are called the associated Legendre functions. And what they are is usually a polynomial in cosine of theta, multiplied by sine of theta if m is odd, or not multiplied by sine of theta if m is even. So it's going to be polynomials in cosine of theta, possibly times a sine of theta, where theta is the usual variable. Those are called the associated Legendre functions. Let's just look at what some of them look like to try to get some idea of what we're dealing with. You're starting to see things that look like pieces of hydrogenic wave functions. And so this is, we're looking here in these diagrams, z is upwards. So the angle theta is varying from 0 to pi as you go around in this direction, right? Theta equals 0 is upward. So it depends on the value of L and M. We're going to put some restrictions on L, and also that will put further restrictions on M in just a second, but just for a sampling of them. If we look at, for example, this one here, just as a non-trivial example, P, so when we write this down, this lower subscript is called L, that's one related to one of our separation constants, and M was related to the separation constant M squared. So we call this PLM, L is 2, M is 1. It ends up, it's 3 times the sine of theta times the cosine of theta. That's supposed to correspond to this graph over here, and it does. I mean, you can think of, where are the zeros of sine of theta times cosine of theta? Well, sine of theta is 0 at theta equals 0 and at theta equals pi, right? So it ought to have a 0 in both those locations. And the way we're drawing this is we're saying, this is not the ordinary graphing of a function. We say, as a function of theta, we're going to go out farther in R the bigger the function is. So we're saying at theta equals 0, this function has value 0 because you don't have to go out at all. Then it gets big at pi over 2, and then, at pi over 4, and then gets small again at pi over 2, and big at 3 pi over 4, and then 0 again at pi. Why is that in terms of the sine and the cosine product there? So I feel like I'm talking too much, so somebody put it into words. Why does that graph over here make sense in terms of this form of the function there? Just to make sure we know how to read those graphs.
It's going to go to 0 every time either sine or cosine.
All right. So the sine goes to 0 at 0 and pi. That means it should have a radial position of 0 at theta equals 0, and theta equals pi is down here, right? And also the cosine goes to 0 at theta equals pi over 2. That's out here. And so we're just drawing how big it is. It's somewhat maximal in between there at pi over 4 and so on. So that's sort of graphing just what happens as you move along in this direction. Sometimes people draw radial graphs of functions that way. Maybe you saw those in one of your math classes, I don't know. Okay, so what about continuity for this function? Well, if we want psi to be continuous, all of these product functions have to be continuous. And this argument requires that, I'm not going to go through the details here, but L has to be an integer. L can't be anything that's when I say an integer, I mean a real number, but also an integer real number. Otherwise, we'll find that the series solution diverges as theta goes to 0 and theta goes to pi. And if it diverges, right, if this function theta as a function of theta goes to infinity as you go up to 0, it's not going to be continuous there. And that means our whole function is not going to be continuous there, right? Anywhere you have some asymptote where the function shoots to infinity, that's not a point of continuity. And we said our wave functions always have to be continuous. So L has to be an integer. Furthermore, you can show that when you look at the negative L solutions to this, you get exactly the same thing as the non-negative L solutions, right? So when you choose L equals -2, it's exactly the same kind of function corresponding to L equals 2. I'm not claiming that's obvious from what we looked at here. And therefore, it suffices to only use L non-negative integer, right? L has to be 0 or 1 or 2. The restriction to those L values then affects what M values can be used. We already said M has to be some integer, but now we find out that your function won't be normalizable unless m is between minus L and L, including minus L and L. Okay. Otherwise, we'll find out that the function actually is identically 0 and it's not normalizable at all. I didn't show any of those details. It comes out of the series solution. So you got to legitimately write down a series solution, get your recursion conditions and all that stuff that I assume you did once or twice, probably in easier cases back in differential equations. Usually they don't have enough time to do a whole lot of series solutions. We'll see some series solution stuff in a little bit more detail when we solve the hydrogen atom, but here I'm just sort of hand waving over it. And I don't think Griffith spends a whole lot of text time explaining it. Okay, so again, the final restrictions on the value of L, that separation constant, corresponding to the separation constant L times L plus 1, is that L has to be a non-negative integer. And then once you know L, M has to be between minus L and L. So if L is 2, then M can only take on the values minus 2, minus 1, 0, 1, and 2. Once we've solved those, with these restrictions, that M and L have those restrictions up there, then for those cases, these functions Y, L, M are called the spherical harmonics. The Y, L, M, the L and the M correspond to the L and the M corresponding to those associated Legendre functions. Okay. The nice thing about them is they appear all over in physics because they didn't depend on the potential here, and they actually come out of other partial differential equations too. So they end up being very generically useful, not just in quantum mechanics and not just in the hydrogen atom or something like that. Finally, how do we normalize these? Well, you might think, we got to take the whole function and normalize it. But the usual approach is, well, if I normalize pieces of this along the way. In other words, if I say that as you integrate over the range of theta and phi of the magnitude squared of just capital theta times capital phi, and you require that it's equal to 1, then I have a simpler normalization condition for this, because I can say as long as I normalize R2 when it's integrated over its range of R values, the whole thing will integrate to 1. So we're going to sort of have a condition for normalization of the spherical harmonics as we go. So in terms of the whole function psi, I have to integrate over all space. Not sure why I can't see that down there, but when I integrate over all space, is it the bottom of my window? No. I guess I just didn't paste it far enough. I have to integrate times dv in spherical coordinates, a little differential volume, right? R squared sine theta, dr d theta d phi, your old friend from three-dimensional calculus. And we can, when we integrate over all space, we can integrate from R from 0 to infinity, phi from 0 to 2 pi, and theta from 0 to pi. And we can divide out, or separate out, factor out the R part into an R integral and this integral. So our goal is going to be, let's normalize these things and see, then at least we're partway towards normalizing our functions. And maybe it's a good place to stop there because I need to hand back the exams. Alvis, let me just apologize to you now. I'm not ready to send back your exam, but I will be by tomorrow. But everybody else's paper exams I graded. So I'm going to pass those back now, and we'll do a worksheet associated with this normalization process for the spherical harmonics on Wednesday. All right. And I've already put this morning, I put the solutions to the exam on the website. So you can go ahead and take a look. Let's see. Jake Woosley. Jake Woosley, if you're in on Wednesday, you can pick it up. Is that okay? Not sure if he's there. Kai. Riley. Your extra piece of paper is still floating in there.
Sorry. Yeah, that's okay.
Yeah, okay. So I've got it here. I'll just give it to you on Wednesday rather than scanning it. Tanner, Yichen, Jake, Fowler. Yeah, overall, I mean, I don't have any real comments about it. Overall, the performance was really good, and I can't remember if there were any particular problems that gave people trouble. Certainly not in general. Maybe the one on the generalized uncertainty principle a little bit, or maybe the last one. And mileage varied on the very first problem of the proof. It seemed like people either pretty much knew the proof or they didn't really know which way to go at all on how to prove that. But that was one of the things I mentioned that you should know for this exam. So if you have any questions when you look at the solutions, let me know. Tomorrow, I'm not planning to hold office hours just because it's a break day and we're not supposed to be really working at all, although I know that's somewhat of a joke always, but hopefully in as much as possible to take it seriously, I'm not going to officially hold office hours. Okay, if you haven't read and posted on this stuff at the beginning of chapter 4, please do that. That can be, you know, an enjoyable little bit of reading you could do on break day, just to relax and forget about classes totally. And I look forward to seeing those and responding to them on Wednesday. Sorry about me just talking so much today, but we're pretty much to the end of that storyline there.